if this thing can. Pointer.
Oh,
I've never tried it before, but we'll see. Does that work? Yeah.
It does work.
Okay, cool.
Fantastic. Okay, awesome. You're set. Good to go?
Yeah, sure.
Okay, so then I'm happy to introduce John Wilkening from Berkeley. We'll hear about standing waterways.
Great. Well, thank you very much. It's great to be back at the Fields Institute. I realize it's been like 21 years since I've been here. So it's, anyway, I'm having a great time this week seeing all the talks and everything. So thanks for organizing this. Okay, so I've been interested in standing waves for a long time, maybe 15 or almost 20 years. This is a photo that G.I. Taylor made. He was sort of interested in the highest wave and seeing if it was really going to form. And so he built a wave tank and actually did it. So I thought that was very cool. I think he was a reviewer on Penny and Price's paper in which they were proposing that. Let's see what's going on. Okay, so what I'm going to talk about today is semi-analytic expansions. These go back to Schwartz and Whitney from 1980 and 81. And then those expansions were proved not to have a problem. Schwartz and Whitney had a conjecture that they would exist to all orders, but they could compute them to 25th order. And then Amick and Tolan actually proved that they won't break down, but they couldn't show whether or not the series would actually converge or not. And there are a lot of reasons to think that it won't. But so anyway, Ahmad and I have been doing high precision computations of these things and studying them and trying to go beyond the series itself and look at Pade approximations of these series and just try to get a better handle on all of these things. So in most of my previous work, I've always computed standing waves using a shooting method. Actually, the first slide here is actually about traveling waves. So this is, since we're doing asymptotic expansions, which is a very old method going back to Stokes. In 1880, he was already proposing that just from a three-term expansion that the highest wave would form a corner. So here, just to show what my movies mean. So I'm showing a time evolution of a traveling wave that's really close to that 120-degree corner. I've color-coded the particles here, which are advected passively with the flow afterwards with the pressure. So you can see that how the pressure changes and how the fluid underneath the free surface actually moves, and you can see it actually drifts and so on. So those are traveling waves, and Stokes conjectured this 120-degree angle, and then it was actually proved to exist by Amick, Frankel, and Toland. And there was also some work just shortly before it was the limiting wave was proved to exist of Longa, Higgins, and Fox that studied the near asymptotic limit, so the almost highest wave. So standing waves are a more difficult beast. There's no frame you can go into in which they become stationary. In a lot of ways, they're similar to your 3D water waves. So you have this extra dimension. In this case, it's time. And so in the 50s, Penny and Price did the same as Stokes and used a fifth order expansion, although there was an error in their expansion. So I think it's correct to third order. And they were proposing that they thought that it would form a 90-degree corner. So I think that was the paper that G.I. Taylor must have reviewed. And then he said, well, undoubtedly, I think it is true. I was unable to follow their argument. So he couldn't really be convinced that it should form this thing. And in my early work in standing waves, I was trying to study that problem. And I showed that it doesn't actually end up forming a corner. Instead, you end up with a lot of high frequency oscillations that show up due to resonances. So it's just a much more complicated story. There's like the self-similarity doesn't end up carrying the day for standing waves, and instead the resonances become dominant at these high amplitudes. So what I want to do today is go back to these previous approaches, more like what Stokes had in mind than the shooting methods that I usually use to compute standing waves, and take this Schwartz and Whitney expansion much beyond the order that they got to, which was like, I think they got to 29th order using quadruple precision in Fortran. And that's actually where you run out of precision in that expansion around with 30 digits of accuracy, somewhere around 29th order. Roberts and Marchand and Roberts a few years later got to 35th order, studying short-crested waves like Eric was looking at, or it's sort of like one of the cases that Eric would be looking at. And so all these expansion methods exist, and usually we think of asymptotic expansions as good for very small amplitude, and then after that you want to use continuation or something. So what I want to look at is like, can you actually use these methods to compute quite large amplitude waves and study their properties? And you can get much more accurate solutions with these expansions. than you can with a shooting method. And so we can start to explore things like analytic continuation and things where you need a lot of digits to not lose them all immediately as you start doing the unstable thing. So one reason people gave up on the expansions is that it was shown by Konkis that the depths at which there's a problem, like a small divisor, are dense. And so there's a real question of whether these series actually converge. And I think they really probably don't converge. Possibly for the infinite depth case of zero surface tension, they might converge. Possibly some of the surface tension cases, as I'll explain, might converge. But for the most part, there'll be divergent series. But nevertheless, the Pet-A expansions can still converge, even if you're approximating a divergent series. So there's been a lot of recent work proving existence of standing waves and more complicated things like time quasi-periodic solutions, like Berkeley earlier this week, and Maspero will talk later today. And anyway, there's a lot of interesting work on Nash-Moser theory. So I want to kind of go back and look at these expansions and see how does this fit in with that? Do we see evidence of the small divisors? How can we get around them? What happens to the convergence of the Pet-A approximations? And also, I'm just trying to piece together, like this is a function of space and time and amplitude. So how do you do these multivariate rational approximations? Like if you do Pet-A and epsilon, do you do it one component at a time, or do you try to put it all together as a single solution, a single expansion? So those are the questions that haven't really been looked at before. Okay, so equations of motion, probably most of the audience is familiar with water wave equations. So I use zeta for the free surface and phi for the restriction of velocity potential to the free surface. If it's irrotational, then it's a potential flow. And the kinematic condition is that the normal velocity of the fluid is the same as the normal velocity of the curve. So that's sort of dictated by physics. And then there's the Bernoulli equation as well, which is equivalent to the Euler equations. And this is what it looks like. If you're moving along the boundary, as if you're like we're doing here with restricting phi to zeta and t, then there's this convective term that's added to the Bernoulli equation here, or subtracted from it to get the phi t here. And so this equation and maybe it's on the next slide, and that equation are the equations of motion. Schwartz and Whitney, sort of long before Dyachenkov and Zakharov were, I guess they had a critical observation that made it really practical. But Schwartz and Whitney also knew how to use conformal mappings and do expansions of the solution. And so they worked out the complete expansion this way. So I'm writing down the notation roughly of Schwartz and Whitney here. So the kinematic condition ends up looking like if these are analytic functions, so we have a conformal map from the lower half plane onto the fluid domain. I guess I should be using the pointer here. So if you have this mapping from the lower half plane to the fluid domain, then the normal velocity looks like this, and then so d phi dn is the normal velocity, but then because phi and psi are related by the Hilbert transform, or they're conformally related, then the conjugate function, a tangential derivative of the conjugate function is the normal derivative of phi there. And so you end up just being able to take alpha derivatives, just plain derivatives of things that you have on the free surface. So that's the first equation, the kinematic equation. And then the Bernoulli equation is a little bit more complicated, but eventually it will boil down to things that are defined on the surface as well. The gradient is phi x plus I phi y, but then you can replace phi y by minus psi x in the using a Cauchy-Riemann equation, and so then you can express the fluid velocity as the conjugate of phi w over zw. So the fluid velocity, that's a physical object. So Schwartz and Whitney non-dimensionalized. I mean, this is a natural thing to do. Then all of our functions will be defined on 0 to 2 pi in space. And then they introduce a period here and have the non-dimensionless t go from 0 to 2 pi. And so z will be defined on the 2 torus, except that the first argument there is a complex variable. So anyway, w is going 0 is in the lower half plane, but it's periodic or z is a periodic function of w with period 2 pi. And then capital W here is the fluid velocity, or the conjugate of it is the fluid velocity. And then I'm doing a couple of new things that weren't done by Schwartz and Whitney. So I'm showing how to expand in the finite depth case, and I'm showing how to expand in the case of surface tension. So we need a curvature to deal with the surface tension if that's turned on. So these are the equations. We have introducing this auxiliary variable W introduces an equation. And the reason to do it is it keeps everything else quadratic, basically. So you have like products of or up to conjugation. Everything's just products of two things. Whereas if you don't introduce this formula, then you'll have a more complicated formula involving divisions and things. Whoops, sorry. Okay, so what Schwartz and Whitney next do is take these equations and then plug in an ansatz for what the standing wave is going to look like. They're in the B equals 0. The B is the bond number, so that's the well, I guess it's 1 over the bond number if you're a physicist, but it's proportional to tau. So tau is the surface tension. So if surface tension is 0, then B is 0. That's the dimensionless surface tension parameter. And the depth I'm calling mu0 later when I introduce the expansions, the fluid depth. So in the infinite depth, that's what Schwartz and Whitney did. So they will have Z being this sort of linear term W. So that causes the parametrization of the curve to increase by 2 pi when you increase alpha by 2 pi. So that's sort of preventing or actually parametrizing the fluid that's also 2 pi periodic. And then they propose this expansion in powers of e to the minus IPW. The reason to use the minus IPW is so that when the imaginary part of W goes to minus infinity, then this thing decays to 0. So in the lower half plane, you want negative powers here. And if we were representing a upper half plane problem, then you'd want positive powers there for the expansions to be convergent in the fluid. And then we do similar things for W and F. In finite depth, we replace the complex exponentials here by sines and cosines, and we pick the sign here, and well, I guess both here and here. I guess both sines and cosines do the right thing when you get to the bottom boundary. So the imaginary part of the fluid velocity on the bottom boundary is 0, so the fluid doesn't flow through the bottom boundary. And then the imaginary part of the this version of the velocity potential is 0, which is basically saying the stream function is constant, or in fact 0 on the bottom boundary, which is also saying there's 0 flux through the bottom boundary. And then this parameter mu0 is just introduced by us here, and it represents the fluid depth, so that it's the imaginary part of the conformal map. So if you evaluate this thing at minus beta, let's see what is going on there. I think maybe I made a mistake. I think I need to evaluate on the bottom boundary. Oh, I guess that's what this is. On the bottom boundary, you'll get minus mu0 here, and so that ends up physically being the depth. So I will expand H in powers of H of t in powers of mu, or with parameters mu, and so the first term happens to be mu0 for the depth. Okay, so if we're going to do surface tension, we have to have a curvature, and I'm sort of following the lead of Schwartz and Whitney to introduce a bunch of intermediate things so that we only ever have quadratic products to multiply together. So that's more of an efficiency computer science approach. Try not to have more than a double sum, just so you have less really big expensive calculations when the order becomes high. So I introduce a bunch of auxiliary variables. The A, B, and C are the ones that Schwartz and Whitney had. I just kept going D, E, F, G, H to expand various things. Eventually, H is expanding the curvature here. And unfortunately, H is also the depth in the finite depth problem, but the two papers are separate papers. So anyway, sorry about that. Okay, so the governing equations, we have these already. So now we're going to plug in our expansions. And at this point, these are functions of time, and the AKs are functions of time. We've taken the spatial part here, but we've left them as time dependent. So when we multiply these together, when I have a sub t or a sub alpha, those things will be, the alpha derivatives are fine because they'll just bring down various powers of, or multiples of p, or powers of p, or products of p. And the time part is still in the coefficient, so we'll introduce the times later. So multiplying these things together, whenever you have like z alpha, z bar t, you'll end up with alpha derivatives introduced like k AKs. The kth component of this thing had an e to the minus well, if it were p, it would be e to the minus pw. So if I take a derivative with respect to alpha, which is w restricted to the free surface, you'll end up bringing down a p. And so I switched the variable to k here inside the sum. So that's where the k's are coming from. Those are wave numbers, so k is a natural letter. And then yeah, so whenever you have a conjugate, so the products end up kind of getting mixed up in a different way, and you end up with a p plus k instead of p minus k's. But they basically look like convolutions, or these sort of reverse convolutions where it's bk times bp plus k. So those are the governing equations for all of the cases. And then there's some factors of 1/2 that come up whether or not there's like a conjugate point that's also being represented by the variable. So when p equals 0, there's often a special case to deal with. So that was notation of Schwartz and Whitney too. In the equations, we have to get down to the curvatures eventually. So the more complicated equations, you just have to go through the definitions and figure out what happens to compute the curvature eventually, and you'll end up with equations and a bunch of products of all of the coefficients that have shown up in the series. Finite depth is uglier because of all the sines and cosines, but you can still do it. My student actually is the one who did the finite depth case, and I did the infinite depth with surface tension basically for the derivations and the coding. And so he managed to keep track of all of the details of how the expansions work in finite depth. Although he left triple sums in places later on, which we eventually got rid of to be more efficient. But they are at least mathematically correct. So the next thing we do is expand our terms in powers of epsilon. So the S thing, that was the period expansion. I probably should write down the expansions on the board too for what they all mean. I'll do that in a second. So I expand. This is essentially the period. It's the it's one of the terms that we use to non-dimensionalize. And so square root of S times 2 pi is the period. So these numbers are giving you how the period is changing. H of t is how the depth changes. An interesting aspect of the conformal mapping is to maintain constant depth in physical space. You actually have to have the depth in conformal space evolving in time. So that was a very interesting challenge in getting these expansions to work. And then we assume various ansatz for the coefficients in how they are going to depend on epsilon. And later we'll also figure out how things depend on time. I'm introducing some notation. E sub nu. Nu is the order of the expansion. So at a given order, it's order nu. And then E sub nu are the numbers between minus nu and nu, where you're skipping every other one, starting at nu. So these are the integers that have the same parity as nu and are less than or equal to nu in magnitude. That's the E sub nu coefficient. And a lot of our sums will be sums over EP plus 2n, which is just the order where you're only including every other term in the expansions. The B's have odd symmetry. So in time here, these are even functions, and the velocity potential is expanded in odd orders. So most of the things end up being even functions of time, most of the coefficients, and then the B's are odd B's and C's are odd functions of time. So B again was the velocity, and C's were the velocity potential, and all the rest had to do with spatial degrees of freedom and intermediate quantities in order to get to curvature, which was the H part. Okay, so those are the expansions. Basically, it doesn't matter too much the details, other than that we've expanded in terms of time through these cosine expansions, and or actually I prefer the exponential expansions. And then space was an initial ansatz to make sure that things were analytically well behaved, become constant as beta goes to minus infinity. And then epsilon, which is the amplitude of the wave. Oh, and by the way, the definition of amplitude of Schwartz and Whitney was the wave, half the vertical crest to trough height. So Z00 is at t equals 0 when the wave is at maximum amplitude. That's the vertical height there, and then at pi, that's the min. And so at that moment in time, that's what they're defining epsilon to be. So we just use that also. Okay. So yeah, so here, this is just a picture of what E sub nu looks like. It's just the set starting at going from minus nu to nu, including the endpoints. And then for the finite depth case, you actually have to worry about expanding sinh and cosh of an expansion. So we're using beautiful theory of Bell going back to the 1930s, how to expand an exponential. These Bell polynomials are the way to do it, and then you can just get the quotient-Cinch expansions from that theory. Just well, actually, we just represent them in terms of the E expansion. So we compute these guys, we compute the B's, and then we get those guys just by using formulas like these formulas in terms of the B's. Okay, so after you've written down on all your ansatz, now you have some ODEs for the coefficients. I think maybe I should write down the formulas on the board, just a few of them, just so that you remember what they are, because I think it would be hard otherwise. So we have the conformal mapping. So the half plane here. This is the W plane. This is alpha and beta. Those are the parameterization. Then the conformal map here. Here's the water wave. It's periodic as well. Period 2 pi. So this is x and y. The dimensionless conformal map is capital Z. So there's the linear term, which is causing, as you increase alpha by 2 pi, it will cause, you'll go through 2 pi here also in the real direction. And then the expansion, I kind of prefer this method now that I've introduced all of the terms. Let's write it as the order on the outside instead of the Fourier mode on the outside, and then I'll sum over P next. So this is the spatial mode, P equals 0 to nu, and I'll put a prime on the sum to indicate that I'm only going to include terms that have the same parity as the upper limit. And then inside of this sum, we have the sum over J and E sub nu, and this is the temporal dependence. So I have A, P, J, and then I put a nu up here, e to the I, j, t. So that's the time dependent part. So that could be like a p, j of t, or a nu p of t. And then s to the p, so the s is going to be e to the minus I w. So there's another conformal map where you can just map this to the unit circle, which I find useful a lot. When I start doing AAA approximations of things, it's actually easier to do here than here. So this is the S plane, this is the W plane, this is the Z plane, and then here's the epsilon part, so epsilon to the nu. And then we also have the expansion for F. So F, what is F? So we have phi equals F over square root of S, and F was the dimensionless velocity potential. But the real one that we're going to use, that if I want to compare to my standing waves that I compute, actually, this is the thing that I compute through shooting. So I have to be able to get that back. So that's just a composition of series in the end, or I mean, sorry, a division of two series. The formula for F is similar, but it doesn't have this term. This one also starts at nu equals 1, goes to infinity. We have a sum over P again. This time we have the sum over J and E nu, but the coefficients are C, CPJ. So those are the C coefficients, e to the IJT, and then we have S to the P and epsilon to the nu. And the T, that's the period of the wave. T is 2 pi squared of S, I believe. To find it here, but that's my memory. And then S has its expansion in sigma n's, epsilon to the 2n. So nu is 2n. In general, nu is p plus 2n. That was the Schwartz and Whitney and Amick and Tolan expansion ansatz. And yeah, I already said what phi was. So hopefully this is helpful. So these coefficients are the ones for the conformal map. These coefficients are the ones for the velocity potential, and the sigmas are the coefficients for the period. And then all the things D through G are expansions for things that are just a method of computing the curvature. So they're not, the intermediate ones aren't really important. But the point is that you end up with only quadratic products and things if you introduce those extra variables. Okay, so once you've introduced the ansatz, you plug it into the equations of motion, and you'll end up with a bunch of ODEs. And the ODEs only involve products of these things, and the B's there are like these guys. They're they're these. I guess I put the new up here instead of a comma n here because once I introduce new, then new is p plus 2n. So you could just do new minus p over 2 as the second component. So a new p, I could write that too. Most of the talk is using the Schwartz and Whitney and Amick and Tolan notation, but it would be like this. So this is normally a p and j. So those are the coefficients. So yeah, question.
Are the two s's the same?
Those s's are the same. The s's, so this s and this s are yeah, those are the same.
There's another s.
Oh, sorry, capital S. Yeah. So this is just like, yeah, just a small s. Sorry about that. Yeah, this s is actually just another variable. I wasn't sure what to call it. And so in the code, I was using s. All right. So we have these ODEs that show up from the fluid dynamics. And they involve products of things. And so we end up having to do a bunch of lattice sums. And so there are two types of things that come up, depending on whether you had a product of a function and its conjugate and another function that was conjugated or not. You can end up with sums that look like regular convolutions like this, UK VP minus K, or they can look like sort of a funny version of the convolution where you've added instead of subtracted here, so UK VP plus K. At first, you'd think this would be a problem, but it turns out that the VP plus K part actually still only involves a finite number of terms at a given order. And so the two formulas for the ultimate, the formula for the products there to get the new lattice sums end up just being double sums of things. And you can pictorially look at them. This looks like a convolution, a 2D convolution, just literally the normal way of doing a convolution. And this one ends up being sort of a shifted thing where you take the lattice points of one and the lattice points of the other, and you match them up. So you're doing convolutions in time, but the spatial part ends up sort of matching up in a non-convolution looking way. But it's still a finite sum at each order. So anyway, so those are the kinds of things that have to be done to compute the forcing terms that are showing up over here. I think of like this is the ODE, and then you have a bunch of lower order terms that end up being driving the ODE at a given term. So this picture is roughly a picture out of Amick and Tolan's paper, maybe even Schwartz and Whitney's too. So to figure out like what the solution is at this point, you'll have all of the entries, all of the coefficients at the previous values of p and n inside of this shape that actually are involved in the formula that is forcing that term. So it gets expensive as things go on out. You have a lot of these little sums to do, but it's very parallelizable. So that's why we could get to very high order. So the governing equations ultimately end up being ODEs. Okay, so if you're going to define the amplitude of the wave to be the vertical crest to trough height, then you'll end up with a constraint on the AP on these terms, so that when you evaluate this series at alpha equals 0 and t equals 0 and subtract it at alpha equals pi and t equals 0, you'll end up with the number epsilon. So that thing here is just enforcing that definition of what epsilon is. And then for the other ones, you'll end up with systems of ODEs connecting A's and C's, basically. And then the driving terms are computed from previously known things. So sorry, it's getting very technical, but for the infinite depth with surface tension, there's a lot more driving terms. I was largely just continuing on from where Amick and Tolan left off. So they had T3 and T4 and T2. They left T1 unused. So we used that for the depth, and then T5 through T9 or something I used for the surface tension. And eventually you end up with formulas that are all manageable. You go order by order. So at the 0th order in our big lattice, the 0th order actually tells you that these two coefficients are 1 and everything else is 0. This is like an arc length expansion, and this is I forget what that one is right before you get to the curvature. At the first order, that's when you start to this one is imposing that the amplitude of the wave should be what it is, the vertical crest to trough height. The solution is just sinusoidal at that point, so that's sort of part of the reason you put the 1/2 in the formula. So A10 ends up being cosine t, B10 ends up being sine t, C10 ends up being minus sine t. And then this is where you find out what the leading term of the surface tension expansion is. So then we have our ODEs, which I'm thinking of as a system of ODEs. These driving terms are computed. I think what Amick and Toland's contribution to Schwartz and Whitney's work was to prove that you'll never end up with this being singular and this not being in the range of that operator at a certain point. You would normally like to, so you actually often have to choose the next sigma in order to solve a compatibility condition here. And there's one place where you don't have a parameter, and that was the one that Schwartz and Whitney were worried about, and Amick and Toland found a really ingenious way to show that it works. So anyway, so at some point you have these numbers, and these things could become very small, or they could become zero, and these are the so-called zero or small divisors that show up in asymptotic expansions of standing waves. So just looking at the determinant of this matrix, this thing is, well, okay, I guess I already eliminated it, so it's clear what has to be non-zero in order for the matrix to be invertible. All right, so resonant cases. So that this in the finite or infinite depth case with bond number being zero, you'll have lambda pj as p minus j squared. So that thing definitely has a lot of zero divisors. But they showed a way to, well, so what you then have to do is figure out what can you do at the previous order in order to make the equation solvable at the next order. And so that was, I think, a really difficult thing that Schwartz and Whitney worked out in 1981. And they weren't sure that it would always work, but every case they got to, they could actually do it. And then, yeah, it's been proved rigorously. But what we've done, or what I've done, is shown that even in the positive bond number case, there are some cases where well, okay, often, there's an exact resonance only when the bond number happens to be of this particular form. So that those things are all rational. So if B is irrational, then there's not going to be a zero divisor. So in the same way that Schwartz and Whitney, or that Amick and Toland said Schwartz and Whitney's algorithm will never break down, this will never break down either. But you could divide by a very small lambda. Maybe this thing could become arbitrarily small. Then you have these small divisors to be worrying about. But I noticed that this is actually, oh, sorry, I think maybe I have another slide here to explain this. So when B is greater than zero, you can get an exact resonance only when B is has this particular form. J and P have to also have the same parity for them to show up in the same equation. So there's no exact resonance if B is rational, and there's also no resonance if there are no integral points on this elliptic curve. So one of my colleagues, Ken Ribbett, is a number theorist, and I was telling him about this problem, and we kind of realized that the elliptic curve theory that he's very famous for is actually very relevant to this problem. And there are a lot of choices of B for which there are no zero divisors. Or there are no small divisors. There's actually a lower bound on how small the lambdas can get, and they never become zero or not. Or Sage can check them, and Sage often fails because it's actually, I think, there's no known algorithm. It may actually be provably impossible to come up with an algorithm to check it, but Sage can often figure it out and determine whether or not there will be any integral points on this elliptic curve. So what I've been doing is, I mean, sometimes I was checking what happens in the exact resonance. Do you have this situation with Schwartz and Whitney where you can do something, and it turns out never. Like if there's going to be a zero divisor, the algorithm just breaks down at that order, at least everything I tried. But we can often go and pick a rational choice of B for which there will not be any resonance or any small divisors at all. And in the finite depth case, I have a feeling I'm going to be running out of time a little bit. So let me just say that in the finite depth case, instead of an elliptic curve, we end up with this ratio of tangents that you have to worry about. So as P goes to infinity, both of these tangents will go to 1 really quickly. Well, actually, sorry, the top one will go to 1 really quickly as P goes to infinity. And so you're really worried about P over tangent mu 0 minus j squared being close to 0. And it turns out you can't avoid that going to 0. For any depth, there will be cases where this goes to 0. And that was something Konkas showed in the 60s. Okay, so finite depth forcing terms are pretty ugly. This quadruple sum is a killer, very slow. So we've since realized that you should introduce a bunch of intermediate variables to never have more than a double sum, and that actually makes a big difference. I proved a theorem that looks at how many parameter, or for what, how common is it to have a problem with the small divisors, And so it turns out that in spite of the small divisors, they decay very slowly for the most part. So for almost every depth, the set of depths for which the things decay greater than some p to the minus 1/2 minus delta is only slightly worse than 1 over square root of p. The set of mu's for which this inequality holds it has Lebesgue measure 1, as long as delta is greater than 1/2. So it has full Lebesgue measure. Oh, delta greater than 0 has full Lebesgue measure. Delta greater than 1/2, and mu 0 is rational. Then mu 0 actually won't have a problem. So every rational number is fine. I couldn't prove that it goes to 0 faster than p to the minus 1, but in practice it seems to also be p to the minus 1/2. So anyway, I was learning a lot about number theory in order to understand this stuff. And there is an asymmetry, and this is sort of interesting, that though the resonant depths are dense, as you take, let's see, so what am I doing? So A goes to 0 as mu 0 goes to a resonant depth, but A stays greater than 0 for fixed rational mu 0. So even though the problematic depths are dense, for a fixed value, you'll have this number be positive. All right, so what do these things look like? So let me just show you, like, I did a big experiment to see like how fast do the zeros show up, and it turns out they follow this p to the minus 1/2 curve really accurately. And obviously, like, I'm stuck at 640th order, so like nobody's ever going to be out at the 10 to the 22, p equals 10 to the 22. So this is really academic out here. But I think the fact that these things are only decaying like p to the minus 1/2 is actually means that the small divisors are fairly tame. Okay, so numerically, we have all these lattice sums. It turns out we thought of a better way to do it than the 1D FFT eventually. Like, each of these products can be done with an FFT. It's just each guy corresponds or has some complex exponentials associated with it. So when you multiply them together, you can take the FFT of both, multiply pointwise, and take the inverse FFT. So that speeds it up. And in fact, the entire thing, both in time and space, you can do with a 2D FFT, which I realized and implemented, and that actually makes a big difference. So to evaluate all those lattice sums, you can do it by writing the expansions like I did here. And then when you have to multiply various terms together at different orders, they're actually two-dimensional functions of e to the ijt and e to the minus iw p. And those products can also be done on a two-dimensional FFT lattice, which saves a lot of time. We do it in arbitrary precision using MPFR, so that is arbitrary. So we've used as many as 4,500 bits of precision, which is like 1,350 digits. And in order to get all of the Pade expansions after you compute, you lose a lot of digits on the way, and then you do something unstable at the end too, which is compute like continued fractions from the coefficients. But we can keep track of everything and see how bad is it, how bad are the floating point errors, and then determine whether we still believe the calculation at the end. And I also wrote this library of how do you pass an MPFR number to another processor, and so we have to export them as text strings, and that actually worked out really nicely. This was the first sign. So this calculation I did in 2014 actually, where I was looking at just the Schwartz and Whitney thing without any finite depth or surface tension. So we have these are the growth rates of the coefficients. So what am I doing? Oh, actually, I'm just looking at the sigma down here, and then up here I have the sum of the norms of the APNs. And when I didn't have enough digits, you'd start to have the modes just start growing fast again. So like with 108 digits, which is the first thing I tried, you didn't have to, I guess a little over 100th order, it started to grow really quick. Schwartz and Whitney only used 30 digits, so they had a problem already at 35th order. And if you want to get out to 600th order, then it turns out, like, it looks like you're okay here, but I needed more than, I think I needed 1,350 digits to be really confident in the answer. In terms of running time, parallelizing it made a big difference. It took 3 days to get to like 480th order here on a single workstation, and with the naive algorithm, and then with the 2D FFT and the supercomputer, then it's 6 hours on to 640th order. Okay, So floating point, if you run this calculation twice with different precisions, or if you do it 3 times, then you can check that the self-consistently, like if you do the difference of these two and look at the error, and then you add more digits, it just shifts down by the amount of digits you added. So there's no I guess the errors are just showing up more or less linearly. As you add digits, the errors decrease linearly, and the losses are sort of built into how much you lose. So you need a certain amount of digits, and then after that, you're just getting more accuracy for the extra digits you're throwing in. These are the norms of the things, and how fast are the. So this is like what is the radius of convergence of the series. So like if you're going to do the ratio test or something, here I'm separating even from odd. So I look at a nu over a nu minus 2 for the norms. You'll end up with so at mu 0 equals infinity, it just never, it stays really nice. It's like 0.3 or 3, I guess, for the radius. Here, these other ones, as you're going along just fine, then you hit a resonance, and then it jumps up to a new level and sort of hits another steady state there. 3/5 hit a big resonance here, and then it kept going. So those are the effects of the small divisors in the growth rates. Like you just get, yeah. Mu 0 is the fluid depth. Yeah, great. And so mu 0 equals infinity is the infinite depth case, and that's the Schwartz and Whitney case. Here are the small divisors, just looking at which ones are the small ones, so you can identify them, and then when you look at the results, each of the small divisors tends to cause a disconnection in the bifurcation curves. So this is a mixture of shooting method and expansion solution. So I'm looking at here, this is a curve of the 7th Fourier mode of the velocity potential versus the amplitude, and you end up with a disconnection in the curves here. If you keep going, let's see. So it's actually the same set of solutions, but some of these disconnections are not visible here. They're kind of all piled up in that area. So as you go through, you have a bunch of disconnections in the bifurcation curves, and it turns out that the expansion solutions are also predicting these things. But I think I have a movie here to show what the disconnections mean. So this is the highest wave at unit depth. Here you have a k equals 7 mode oscillating on top of the main wave. It goes through 3 oscillations per cycle of the main wave. So this is like a physical resonance, which is causing this disconnection. And if I go back to the previous slide, whatever that is, on one side of the disconnection, you'll end up with the movie I just showed you, and on the other side, it's the opposite, and it has a dimple at the crest instead of a protrusion at the crest. Instead of sharpening at the crest, it flattens at the crest. And so the resonance, the disconnection has to do with how that sort of near small divisor sort of ends up introducing 2 solutions that can have different phases oscillating on top of the main solution. So you can also look, sometimes when you find a potential bifurcation, you don't know what it actually is. So here I'm looking at another one that I found after I had mostly written the paper, and I didn't want to go through all the time of tracking the shooting method to figure out which resonance it was. So I just solved a linear problem and looked at what is a perturbation, what is the smallest, what initial condition, based on the SVD, what has the smallest singular values for the most resonant curve. And it turned out to be something where I could just count off the oscillations. But you see they're very non-uniform. So this is pretty far from the flat water wave. So I think there are, I've forgotten how many there are, 37 and 17 or something oscillations in this thing. But when the wave is high here, the oscillations have a shorter wavelength, and so it's sort of a non. It's definitely far from the flat state, but still kind of the solutions are still basically looking like oscillations on oscillations. Okay, so yeah, so that's what this one was. 2738 is the amplitude where I found this extra disconnection and didn't know what it was. So this is a method of identifying disconnect of what resonance is causing it. Pad A is so if you just do the asymptotic expansions, you'll manage to get, or you'll sort of converge to the very first disconnection, and until you encounter a new resonance, and then it'll start to converge to the next closest one to the origin. So it's kind of useless. Those plane expansions, eventually you have no digit, you have no amplitude left where they're accurate. Like they're super accurate for a little bit, and then you have nothing left after that. Whereas Pad A happily jumps over the curves. So the black dots here are numerical solutions from the shooting method, and then the blue curve is the Pade approximation, and we're actually getting 30 digits of accuracy. We're pretty far out here, jumping across these disconnections. Okay, so to compute Pade, I usually use continued fractions these days. I've done both. There's also like a Toeplitz system you can solve. And I'm expanding Fourier modes in often, so we can compute the expansions of the CPs. So you can compute the expansions of the modes by solving some equations from the expansions that you have, basically. Also, these coasters and so on have expansions themselves. And so let's see. So I'm looking here at how, as you increase the order of the Pade approximation, you continue to the error continues to decrease to 0. The baseline here is what the accuracy of my shooting method, which was done in quadruple precision. So you can't do better than that in the comparison, since the reference solution isn't very accurate. Isn't that? And then here are the resonances where you lose accuracy there, partly because the shooting method is less accurate, partly because it's more sensitive. It's a small value of change in epsilon leads to a large value in the change in the solution. So one thing when I'm looking at the Pade is I found that you end up with, well, here's more standing waves on standing waves being responsible for this disconnection. This was the simplest bifurcation I found, where it bifurcates onto its own self, like you jump over to a path that you could have gotten to going the other direction. We found in the Pade approximations that there's a bunch of Pade poles that are thrown in between these two turning points. And so that looks like a branch cut as a function of epsilon, this is the first time anyone had seen that. In prior work, like Roberts and Schwartz and Whitney too, had seen single poles in their solutions, but no one had ever seen a whole stack of them that look like a Cauchy integral sort of branch cut. Here I'm looking at the exact resonant depth where there's no solution. Can we somehow piece together a family of standing waves varying depth? So this is a birational approximation where I took each of my continued fraction coefficients and thought of them as functions of this depth parameter. Chi is just like chi goes from -1 to 1 as the depth goes from just in the small neighborhood of the resonant depth. And you can see the disconnection just sort of emerging here. And this whole thing, each of them is an accurate standing wave. I think I have 24th order or 20th order approximations throughout that region. And there's a really big disconnection here. So like it's a really nice rational formula showing the effect of the resonance throughout the domain as I vary depth and amplitude epsilon in either direction. This one is looking at what happens as I vary the depth. This is a crazy slide, but as you vary the depth, this thing shrinks to 0 and then disappears. And then on the other side, these guys shrink to 0 and then jump onto the imaginary axis, and you'll get branch cuts on the imaginary axis instead there. Here's another case where it's even clearer about the branch cuts on the imaginary axis. So there's what is this? This is depth 1/16. And so this is what the wave looks like. It's this one's pretty shallow. So you have the standing wave looks like a collision of solitary waves that sort of pops up and then goes back out and then pops up on the other side. And the resonance effect shows up in the Fourier modes like this. That's what that little cascade of zigzags is. And I think that thing is closely related to where this thing on the imaginary axis. Actually, sorry, that cascade is due to this one, which is an actual disconnection. Okay, so yeah, so I'm looking again at the small divisors. They sort of predict what modes are going to be relevant. Here I'm looking at a nearly infinite depth case, so depth of 16, and you end up with everything out here looks like the infinite depth case. These are poles and zeros of the Pade expansions. But then I ended up with this little structure here at the origin, and actually comparing 10, 16, and 4, I found like a formula that seems to work really well. Just guess and check, and eventually I got something that was nice. And it turns out that this structure looks the same at all those depths. It just changes scale and shifts up and down. So you have this little branch structure that approaches the origin here. I just very recently did the same thing with nearly zero surface tension. It's really hard to figure out parameters that are known to that Sage can succeed in saying there's no small divisors and no zero divisors. And anyway, usually it fails, but I found this one that works. And I have this is an amazing branch cut. So this thing is also going to the origin, and it's like it's a very tiny structure that is clearly a branch cut in the epsilon direction. Otherwise, out here it looks like the infinite depth case. So those perturbations actually are pretty different. The growth rates of the A sub n's and so on is huge because of these things close to the origin. These guys cause the coefficients to grow rapidly. But the Pade approximations don't really care about that. Like away from this point, you're still converging with Pade, even though you're well outside of the radius of convergence of the series. So at some point, I was trying to use the amplitudes here to predict the radius of convergence. It looks like I have this many digits when you do the analysis of the extrapolation, but I am very skeptical. I think that probably that there are actually bifurcations here that are just so tiny that you can't that they're not showing up in these coefficients. Okay, so I want to actually, the main thing I want to show you is, this is the thing I did yesterday, was looking at analytic continuation into the upper half plane as time evolves. So what I'm doing here is evolving in time a solution that I computed with the Pade expansions to, I think in order to go that far up, I needed to have about 100 digits of accuracy in the standing wave. So this is analytic continuation into the upper half plane, and then trying to so the black line there is the surface of the water, and then this is what's going on with the poles in the complex. So this is in the S plane here. So I pulled this guy back. Pulled this guy back to here, and I'm looking at the conformal map as a function of S. And then you see this really beautiful branch cut in the S variable. So this is Z as a function of S. You have this branch cut that goes in, and that's what's causing the mesh to kind of split apart here when this gets up to a certain amplitude. So the wave is fine, but if you analytically continue beyond the free surface, you'll end up with this cut. Okay, so I think I'm just about done. So, how did I do that? So I computed the epsilon expansion coefficients at a bunch of points. So it's a pointwise expansion. I used Pade to evaluate those at a desired amplitude. I used 0.4 there, which is beyond the radius of convergence of the thing. So it's a pretty large amplitude wave. But ultimately, after I get the solution at t equals minus pi over 2, which is the smoothest solution, I then actually evolve it in time. So I'm doing a mixture of expansions to compute an initial condition, then evolving to make sure that they're actually standing waves. And it seems to be the most accurate way to do it. And then I use this barycentric interpolation using the AAA algorithm of Trefethen and his co-authors here. As you can see, I have a lot of digits of conserved energy, and the velocity potential actually did go down to 10 to the minus half of this, so 109. Here's the well-resolved Fourier modes of the time evolution. And this is the AAA. So I needed somewhere between 45 and 53 AAA interpolation points to end up with 100 digits. And that allowed us to compute those things. So okay, so I'll wrap up. So what are these things? So is this really a problem? So I think each of these corresponds to some kind of bifurcation. And so what I was doing here is, this was work from 2012, where I found one extra bifurcation in the infinite depth case with zero surface tension, but it was in a tiny narrow window. Turns out Pade sees it, can predict it, can compute it with 30 digits, and it actually sees the resonances. So I think all of these things are actually resonances in the wave that actually should eventually cause this to drop, even though we don't see it yet. Okay, so I will stop there. I've looked at also like a model problem where the series that you're looking at is divergent, but the Pade converges nevertheless. And so like you continue to get exponential accuracy in Pade, even though it has this staircase thing that we're seeing in our standing waves. So I'll just stop there. So thank you very much.
One question.
Could you? I was a little unclear how you were estimating the error of convergence and the floating point error.
Yeah, great. Yeah. with the PAD stuff, you can actually look at the continued fractions as you're going. You can even though they look like the formula goes back to front, you can evaluate them front to back, and you can see how in the recurrence how closely aligned the successive terms are. And so there's like you can compute an angle between them, and so that angle tends to go to 0 really quickly. So I can measure that angle. So that's one measure of error. The other one is to take the PAD expansions at t equals 0 and then evolve them by an independent method, and evolve that thing and see how accurate it is. And so I got this thing, this number that I mentioned here, this f equals 2 to the minus this thing. So this was computed by a time stepping method, whereas the initial condition was computed by PAD. So it was two separate methods that confirm each other. And then for this thing, you look at Fourier plots and just to see if you've resolved the mesh. If it goes unstable, you'll have these things growing out here. So you'll see problems right away. With the floating point stuff, I can run the calculations in over several times with different underlying precisions. And so that's what I was doing with this slide here, this one. So I did the same calculation with 212 bits and then 300, well, let's see which one is which, 212 bits and 480 bits and 638 bits. And then I compute the same numbers. So then I'd take the difference of these two and assume that's the error in this one. And then I can do it again and take the difference of these two and these two and see that this guy agreed about what the error in this one was, and then said the error of this one happened to be the same as the number of extra digits I used. So that was just another self-consistent check. You're right. It's always a question, like you have to just think like, what could be going wrong, and do I really believe this? But I think that having the independent time stepping method is a really good way to be sure that the methods or the solutions are accurate.
And finding the minimum floating point you needed, there was like a blow up then in this.
Oh, right. Yeah. So, right. Good question. So here, this was before I really understood what I was doing. So I saw this kink and thought, oh, interesting. So I assumed at first that this was just what it is, that the coefficients were growing at that rate. But then I tried it again. I'm like, well, let me just add some digits and see what happens. And then it stayed down here. I was like, oh, I guess that was floating point error. And then it went up again, but at the same slope. And so then I thought, oh, okay, that's probably also just an artifact. So I'll do it yet again with even more digits. So one nice thing about MPFR is unlike double precision, where you're just stuck with 16 digits all the time. Like you can just add one parameter and tell it to do it again with a bigger number. And the only thing is that it's more expensive, but actually not that much more expensive. Like jumping from double to quad double is about a factor of 10 in cost. And then going from quad double to any amount of MPFR is another factor of 10. And then going from MPFR with 106 digits to 1,000 digits is probably a factor of 2 or 3. They have really efficient ways of dealing with large numbers. They use FFTs to do their multiplications and things like that. Yeah, so.
Any idea why those lines are parallel?
I don't know. Yeah, that's a good question. Yeah.
Okay, thanks a lot. So
Sure.
I suggest that we save further questions.
Yeah, sure,
for the
sure.
coffee break.
Sorry, I went over.
Maybe we start 5 minutes later as well. Let's thank John again.